Welcome to this explainer. Okay, so today we're going to permanently shatter a misconception that almost all of us carry around every single day. I mean, how many times have you looked at a weather app and complained about the heat when you're technically checking the temperature? In everyday conversation, we use these words like they're totally interchangeable, but in the realm of physics, they are entirely different things. One is an average, one's a total, and one is actually an action. By the end of this explainer, you'll have a crystal clear understanding of the invisible forces running everything, from the thermometer in your bathroom to the fundamental laws of our universe. Let's get into it. Here is our quick roadmap for today's journey. We'll start with temperature versus thermal energy, look at how we measure the invisible, jump into heat and energy, cover the physical effects of heat, and wrap up with exactly how heat travels.
All right, part 1, temperature versus thermal energy. To kick things off, we really need to zoom all the way into the microscopic, particulate level to clear up our first major hurdle.
So what actually is temperature? Well, fundamentally, it's just a measurement of the average kinetic energy of a body's particles. Think of it like a room full of people running around. Temperature doesn't care how many people are in that room. It only cares about the average speed they're running at. This means a tiny drop of boiling water and a massive industrial pot of boiling water, they have the exact same temperature because the average vibration speed of the water molecules in both of those samples is exactly the same.
Now, thermal energy, that's a completely different story. Thermal energy is the total energy a body has due to all that particle movement. It relies on both the speed of the particles and the total number of particles in the crowd. So, going back to our boiling water example, while the tiny drop and the giant pot share the same temperature, the giant pot has vastly more thermal energy. Why? Simply because there are billions and billions more vibrating particles inside of it.
And this really hits the nail on the head. Temperature is what we call an intensive quantity. Intensive basically means it does not depend on the amount of matter present. We pit that directly against thermal energy, which is an extensive quantity. Extensive means it absolutely 100% depends on the amount of matter. Pinning those two concepts against each other really makes the difference impossible to forget. Moving on to section 2, measuring the invisible. So the big question is, how do we actually capture data on these invisible, wildly vibrating little particles? Well, we use thermometers, obviously, but the physical reactions they use to give us a reading are actually incredibly different. Digital thermometers rely on electronics. Specifically, a resistor inside them physically changes its electrical resistance in response to the surrounding temperature. On the flip side, we have expansion thermometers. Think of those classic glass ones. They contain a liquid that physically expands, taking up more volume when it warms up or contracts when it cools down. It's two totally different physical reactions measuring the exact same invisible kinetic energy.
All right, section 3, heat and energy. It's time to introduce the real hero of this explainer, the concept that literally drives the universe forward, heat.
Now this is where the biggest misconception lies. Heat is the transfer of thermal energy. It's an action. It's the movement of energy from a body with a higher temperature to a body with a lower temperature. Seriously, a hot cup of coffee doesn't contain heat. It contains thermal energy. Heat only happens when that thermal energy leaps from the coffee out into the cooler air of the room, desperately seeking balance. And that balance has a specific name, thermal equilibrium. Heat literally only exists as long as the transfer is happening.
Because heat is an active transfer of energy, it needs a unit of measurement. Now, officially, in the International System of Units, we use the joule, but you've almost certainly heard of the calorie. 1 calorie is precisely defined as the amount of heat it takes to raise the temperature of 1 single gram of water by exactly 1 degree Celsius. And for all of you doing the math at home, 1 calorie equals exactly 4.18 joules. So whether you're talking joules or calories, you're talking about the exact same transfer of energy. Next up, section 4, the physical effects of heat. Now that we know what heat is and how to measure it, let's look at what actually happens when this energy transfer physically alters matter. When a body receives or loses thermal energy, basically 3 main physical effects can happen. First, the most obvious one, an increase in temperature. Second, a change of state, like solid ice melting into liquid water. And third, dilation or expansion of the material itself. Let's break these down real quick. If we want to increase the temperature of an object, it's not just a uniform process. It's actually a mathematical recipe that depends on 3 key ingredients. First, the mass. How much stuff are you actually heating up? Second, the temperature increase you actually want to hit. And third, a really unique property called specific heat. Every single substance has its own specific heat, which is basically a measure of how stubborn it is. Some things heat up super easily, while others take massive amounts of transferred energy just to budge a single degree.
But what happens when we heat something so much that it changes state? Let's say we're boiling pure water. As it boils and turns into steam, the temperature stays totally flat at 100 degrees Celsius. It doesn't get any hotter. Why? Because all that heat we're applying is now doing manual labor. It's actively breaking the bonds between the particles instead of making them vibrate faster. This fascinating plateau where the temperature just stops rising during a state change is driven by a property called latent heat.
Okay, so we know things generally expand when heated, right? And usually, as particles lose thermal energy and vibrate a little less, they shrink and contract. But let me ask you this. Does absolutely everything always shrink when it cools down?
Well, the answer is no. And honestly, this exception is absolutely vital to life on Earth. Enter the anomalous expansion of water. Unlike almost all other matter in the universe, when water cools down, specifically from 4 degrees Celsius down to 0 degrees Celsius, it expands instead of contracting. This tiny, weird factual anomaly means that solid ice is actually less dense than cold liquid water. It's the exact reason why ice floats to the top of a freezing lake in the winter, creating this perfect insulating layer that allows all the aquatic life to survive underneath. Pretty wild, right?
And finally, Section 5, how heat travels. Let's look at the actual nuts and bolts of how this thermal energy moves from point A to point B to find that sweet spot of equilibrium.
So, there are 3 primary modes of heat transfer. First up, conduction. This happens in solids. The energy just gets passed from vibrating particle to vibrating particle, but the matter itself, it stays put. Next is convection. This happens in fluids, so liquids and gases. Here where the thermal energy actually hitches a ride on the moving matter itself. Think of hot air rising. And finally, radiation. This doesn't need matter at all. It can travel through a total vacuum, literally like space, as infrared thermal energy moving all the way from the sun to the earth.
We've covered the intensive nature of temperature, the extensive nature of thermal energy, and that relentless transfer of energy we call heat. But I want to leave you with this kind of mind-bending, big-picture thought. Since heat only exists when there's a difference in temperature, constantly transferring from hot to cold to find equilibrium, what happens to our universe in the far distant future when all the energy has perfectly distributed itself and everything everywhere is the exact same temperature? It's a profound, kind of spooky question that really shows the inescapable power of the physics we've unpacked today. Thank you so much for joining me on this explainer, and keep questioning the science all around you.